I am Dr. Muhammad Naeem Azhar, your instructor for the course of mathematics for the classes first year FSC pre-engineering, ICS, and the class of BS Urdu second semester. We were studying exercise number 3.4 in our last lecture, which was on campus, and we restart from this exercise in our online mode. First of all, I have to revise the 4 definitions which were used in this exercise. I have explained in my classes, but I repeat those definitions for your convenience. First of all, we have studied what is a symmetric matrix. A symmetric matrix is one matrix in which if we take transpose, then no change happens, means A transpose is always equal to A. If we find such a matrix in which A transpose is equal to A, then we say that matrix A as a symmetric matrix. And if we take transpose and the matrix A does not comes originally, we have to take minus common from the whole matrix and then A appears. That is, if A transpose is equal to minus A, then we say that matrix A as a skew-symmetric matrix. Similarly, if there are complex entries, means there are imaginary numbers involved in your matrix, then the concept is enhanced to Hermitian matrix. What is a Hermitian matrix? Hermitian matrix is a matrix in which we take conjugate and then transpose of the given matrix, and if after taking conjugate and transpose the matrix is not changed, means A conjugate transpose is equal to A, then that matrix A is called Hermitian matrix. And if A conjugate transpose is equal to minus of A, then that matrix A is called a skew-Hermitian matrix. That is, mathematically, if A transpose is equal to A, then the matrix is symmetric matrix. If A transpose is equal to minus A, then the matrix is skew-symmetric matrix. If A conjugate transpose is equal to A, then matrix is called Hermitian matrix, and if A conjugate transpose is equal to minus of A, then that matrix A is called skew-Hermitian matrix. So we start the exercise from question number 2, which is included in your smart syllabus. If matrix A is given 1 2 0 3 2 minus 1 minus 1 3 and 2, we have to show in this question has two parts. In first part, we have to show that A plus A transpose matrix is a symmetric matrix for this value of A, and the second part, which is solved here, in which we have to show that A minus A transpose matrix is a skew-symmetric matrix. That is, first you have to understand the statement. The matrix A is given. We will find A minus A transpose matrix. Then we will show that the matrix A minus A transpose, which is a single matrix, we can say that matrix is equal to B. We have to say that, we have to show that B is equal to A minus A transpose matrix will be a skew-symmetric matrix. So now we start the solution. We have to prove that A minus A transpose is a skew-symmetric matrix. First of all, we have to find A minus A transpose, for which we take the transpose of matrix A, which is explained here. If A is 1 2 0 3 2 minus 1 and minus 1 3 2, after taking A transpose, all the rows will be changed into columns. That is, first row 1 2 0 will be the first column, and second row 3 2 minus 1 will be the second column, and the third row minus 1 3 2 will be the third column. And after finding A transpose, we can subtract A transpose from A to find A minus A transpose. That is, A minus A transpose can be found in this way. First we place A on the place of A minus A transpose in the place of A transpose. Then we simply subtract these two matrices. Subtraction is simple. First entry will be subtracted from first entry, second will be subtracted from second, and so on. And after subtraction we get 0 minus 1 1, 1 0 4, 1 0 minus 4, and minus 1 4 0. Now A minus A transpose matrix is obtained. Our question was, we have to show that this A minus A transpose matrix is symmetric, is skew-symmetric. If we have to show symmetric or skew-symmetric, then we apply transpose on the given matrix. If now we have A minus A transpose, we apply transpose on both sides. That transpose of this matrix 0 minus 1 1, 1 0 minus 4, and minus 1 4 0 will be on the next page. First row will be first column 0 minus 1 1 first column, second row will be second column 1 0 minus 4, and third row will be the third column of this transpose minus 1 4 and 0. Now we can say that this matrix is not equal to A. We can go to previous page and check that A minus A transpose matrix and this matrix has the difference of minus signs in each entry. 0 is not a positive number, not a negative number, so 0 is considered as 0 null, but all the other entries are different. So if we take minus 1 common from this matrix, then we can get the matrix minus 1 into 0 minus 1 1, 1 0 minus 4, minus 1 4 0 by taking minus 1 common from whole matrix, and we are taking common from the matrix, so minus should be in all entries, and we have to take common minus 1 from all the entries. This is not a determinant. In a determinant we can take common from a single row or from a single column, but in matrix we have to take common from all the entries. That is, this matrix is 3 cross 3, then we have to take minus 1 common from all the 9 entries. Now we can simply say that minus 1 is outside and the matrix inside is equal to A minus A transpose, which was on the previous page. We can say that A minus A transpose matrix is again appeared after taking minus 1 common. So we can use the concept of skew-symmetric matrix, that if A minus A transpose whole transpose is equal to minus of this matrix, then this matrix A minus A transpose is called a skew-symmetric matrix. So we have proved that this is A minus A transpose matrix is a skew-symmetric matrix, and part 1 is not included in your smart syllabus. Now we should go to the next question, which is in your smart syllabus, which is question number 5. In this question we have to show that A into A transpose matrix and A transpose into A matrix. These are two parts. First part is we have to show for A into A transpose, and for second part we have to show for A transpose into A are symmetric matrices for any matrix of order 2 cross 3. If A is a matrix of order 2 cross 3, then we have to show these two parts, that is A into A transpose matrix will be a symmetric matrix, and also A transpose into A matrix will be a symmetric matrix. So we solve part 1 here, which is A into A transpose. First we write A into A transpose and then we apply the concept of symmetric matrix, because we have to show the given matrix as a symmetric matrix. We apply A into the transpose on the given matrix, A into A transpose whole transpose, and then apply the formula of transpose of multiple of two matrices, which is written on the right side in the reason, that is A into B transpose is always equal to B transpose into A transpose. This is formula for multiplication of two matrices and taking transpose of those matrices. So we apply this on our form A into A transpose. We apply transpose, then transpose is applied in the reverse order, that is A transpose whole transpose and into A transpose, And simply, if we take transpose of A transpose, then the matrix A is obtained. That is, we firstly change rows into columns and then change columns into rows. Then we will get the same matrix A. And A into A transpose is obtained. Now compare left and right sides. Left side is A into A transpose whole transpose, which is equal to A into A transpose. Then apply the concept of symmetric matrix. Hence, A into A transpose matrix is a symmetric matrix because after taking transpose there is no change. If after taking transpose there should be no change, then the matrix given is called a symmetric matrix. So our given matrix A into A transpose is a symmetric matrix. This is part 2. In the similar manner, now we take A transpose into A and apply transpose on left side by using the formula given in the right corner. We use and apply transpose on the both given matrices. So we will get the form A transpose into A, and this form is of a symmetric matrix. We can see that A into A transpose whole transpose is equal to A transpose into A. So this is a symmetric matrix. Now question number 6 is also included in your smart syllabus. This question has two parts. First part is included in your smart syllabus, second part is left. So we explain first part here. If A is equal to iota plus iota 1 and minus iota, then we have to show that A plus A conjugate transpose is a Hermitian matrix. Firstly, I explained that this matrix has imaginary numbers, that is complex numbers. When we see complex numbers in a given matrix, then this will be checked for Hermitian matrix, not for symmetric matrix, because complex numbers have conjugate. So we first apply conjugate and then we take transpose. So we have to show that in this question, first part, A plus A conjugate transpose is a Hermitian matrix. So we first find A plus A conjugate transpose matrix. For this we write A, which is given iota 1 plus iota 1 and minus iota. We apply conjugate on this matrix. The application of conjugate is where there are imaginary numbers or complex numbers, we will change the sign of imaginary part of that complex number, and conjugate of a real number in which there is no iota is same as the previous real number. So we apply the conjugate on the whole matrix and we will get conjugate of iota is minus iota, conjugate of 1 plus iota is 1 minus iota, conjugate of 1 is 1 because this is a real number, this has no iota in it, and conjugate of minus iota is iota. And now apply A conjugate transpose. We take transpose of this matrix A conjugate and we will make first row as a first column and second row as a second column. So we have obtained A conjugate transpose matrix as minus iota 1, 1 minus iota and iota. Now we have to find A plus A conjugate transpose matrix, which will be a single matrix. So we add these two matrices, the given A and which we have found A conjugate transpose. We add these two matrices and addition is simple in matrices. The order should be same. Both are 2 cross 2 order. So we add these two matrices as first element is added into first element, second element is added into second element, and third is into third, and fourth element is into fourth. So we will obtain the resultant matrix 0, 2 plus iota, 2 minus iota and 0. This is our A plus A conjugate transpose matrix. Now we have to show that this matrix is a Hermitian matrix, and to show a given matrix a Hermitian matrix, we have to apply first conjugate on the whole matrix and then we have to apply transpose on the whole matrix, then we see the resultant matrix. Firstly, we apply the conjugate on this matrix. The conjugate of this matrix is obtained by applying conjugate on each entry of this matrix. So we have conjugates. The conjugate of 0 and conjugate of 2 plus iota, conjugate of 2 minus iota, and conjugate of 0, which will be conjugate of 0 is 0 because 0 is a real number. Conjugate of 2 plus iota is 2 minus iota because 2 plus iota is a complex number. We will apply conjugate on it and we will get 2 minus iota. Then we will apply conjugate on 2 minus iota. Then we will apply conjugate on 0. The conjugate of 2 minus iota is 2 plus iota, and you can conjugate of 0 is 0. So we will obtain the matrix 0, 2 minus iota, 2 plus iota, and 0. So now we apply transpose on this matrix. After applying transpose on this matrix, first row will be changed into first column and the second row will be changed into second column, and we will get the matrix A plus A conjugate transpose again. So we can see that after applying transpose and conjugate, both operations conjugate and transpose, the matrix is not changed. So this matrix is a Hermitian matrix. So we have proved that A plus A conjugate transpose, which is a single matrix, is a Hermitian matrix. This was part 1, and part 2 is for your self study. Now we have to go to the next question in smart syllabus, which is question number 8. This is an important question because multiplication in this question is tedious. The given matrix A is in this question is, if A is equal to 1, 1 plus iota and iota, then we have to simply find A into A conjugate transpose matrix. We have to simply find this matrix. So for this we have to solve. Solution is A is equal to 1, 1 plus iota, iota. Firstly we find A conjugate, then A conjugate transpose to multiply with A. We find A conjugate, we take conjugate of every element of this matrix. So conjugate of 1 is again 1, conjugate of 1 plus iota is 1 minus iota, or conjugate of iota is minus iota. Then we apply transpose on this A conjugate matrix and we will get 1, 1 minus iota and minus iota matrix. Since we have to find A into A conjugate transpose matrix, so we write these two matrices in their place. First we put A, which is a column matrix, then we place A conjugate transpose, which is a row matrix. We can see that first matrix has a single column, this is called a column matrix, and second row matrix is a single row, so this is a row matrix. Now we have to multiply these two matrices. Before multiplication we have to check the condition of multiplication. First matrix has 3 rows and 1 column, and second matrix has 1 row and 3 column. If the number of columns of first matrix is equal to number of rows of the second matrix, then we can multiply these two matrices. So we see that in first matrix there is 1 column and in second matrix there is 1 row. They are same, they are equal, so we can multiply these two matrices and we have to get the resultant matrix of order 3 cross 3 from here. Now we simply multiply, and multiplication is like we take first row and multiply with all the columns of the second matrix. Then we will take second row and multiply with all the columns of second matrix, and then we take third row and multiply with all the columns of third matrix, second matrix. Now we take 1 into 1, that is 1, 1 into 1 minus iota, that is 1 minus iota, and 1 into minus iota, that is equal to minus iota. Then we have to take second matrix, 1 plus iota into 1, that is 1 plus iota, 1 plus iota into 1 minus iota, that is written, and 1 plus iota into minus iota, that is multiplied. Then we take the third row, iota into 1, iota, iota into 1 minus iota will be iota minus iota square, and iota into minus iota will be minus iota square. Since iota is a complex number which is equal to minus 1 and iota square is equal to minus 1, we can put the values of iota square where it appears. So we put iota square is equal to minus 1 where it appears, and we'll get this matrix which is written on the top of page 5. Now after simple calculation we get the matrix 1, 1 minus iota, 1 plus iota, 2, 1 minus iota, 1 plus iota, and 1. This is the required matrix, and in this question we have to just find the matrix A into A conjugate transpose, which we have found on page 5. This was today's lecture. We will next study the topic of rank of a matrix in our next lecture in